It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last 2 episodes, we journeyed deep inside the convolutional neural network, the architecture that gave machines the power of sight. We saw how CNNs use clever tricks like local receptive fields, filters that act like tiny specialized eyeballs, and parameter sharing to efficiently scan an image for features. We learned that a CNN, which learns to spot a cat's ear in the top left corner of one image, can use that exact same knowledge to spot it in the bottom right of another. This principle, known as spatial invariance, is the bedrock of its power. It assumes that the data is a static spatial grid where the meaning of a feature doesn't depend on its absolute position, only its local context. But what happens when that assumption breaks down? What happens when the order of information isn't just a minor detail, but the very essence of the data itself? Consider the sentence, quote, "The dog chased the cat," end quote. Now let's rearrange it. Quote, "The cat chased the dog," end quote. The components are identical, the same words, the same concepts, yet the meaning is completely inverted. A standard feed-forward network, or even a CNN, would be profoundly confused by this. They process their inputs in isolation, assuming each piece of data is independent of the others. They suffer from a form of computational amnesia, unable to remember what they just saw a moment ago. This limitation isn't a small flaw, it's a barrier that prevents them from understanding language, music, financial trends, or any process that unfolds over time. To see why this matters, you only need to look at the smartphone in your pocket. Type the beginning of a sentence, quote, "I'm really looking forward to the," end quote, and watch the magic happen. Your keyboard suggests, quote, "weekend," end quote, quote, "meeting," end quote, or quote, "event," end quote. How does it know? It's not just looking up words in a dictionary. It's running a model that has learned the statistical patterns of language. It understands that given the specific sequence of words it has just seen, certain words are far more probable to appear next than others. To do this, it needs a memory. It needs to hold the context of, quote, "looking forward," to end quote in its mind, to make a sensible prediction. Today, we deconstruct the architecture that first gave neural networks this crucial ability to remember. We are going under the hood of the Recurrent Neural Network, or RNN. This is the first model in our curriculum that is fundamentally designed to handle sequential data. We will explore how a simple, elegant idea, a loop, allows a network to maintain an internal state, a form of memory that captures the past. We will see how this memory allows it to process the world, not as a series of disconnected snapshots, but as a continuous flowing narrative. This is a critical step in our journey, moving from models that recognize patterns to models that can begin to understand process and context. To truly appreciate the innovation of the recurrent neural network, we must first solidify our understanding of the problem it was designed to solve. The world is not just made of static images or tables of numbers. A vast amount of the data we care about is sequential. Sequential data is any information where the order of the elements is not just arbitrary, but is fundamental to its meaning. The most obvious example is human language. A sentence is a sequence of words. A paragraph is a sequence of sentences. The order defines the grammar, the logic, and the narrative. But it goes far beyond text. Think of time series data. The price of a stock over the last year, the daily temperature readings in a city, or the electrical signals from a patient's heartbeat on an EKG. In each case, the value at any given point is deeply connected to the values that came before it. Audio is another perfect example. A sound wave is just a sequence of air pressure amplitudes over time. Your brain interprets this sequence as speech, music, or noise. Even our own biology is sequential. A strand of DNA is a long sequence of 4 nucleotide bases, and the order of those bases contains the blueprint for life itself. Now, before we go further, we have to ask a practical question. How do we even feed this data into a network? Our models, as we learned in our unit on machine learning, speak the language of numbers, specifically vectors. We can't just feed the letters cat into a neural network. The most basic approach, which you might recall from our early discussions on classification, is called one-hot encoding. Imagine our entire vocabulary has 50,000 words to represent the word quote cat, end quote, which might be word number 8042 in our dictionary. We would create a vector with 50,000 elements. This vector would be all zeros, except for a single one at the 8042nd position. The word quote dog end quote, perhaps word 12,115, would be a different 50,000 element vector with a 1 at its position. This works, and it's how early RNNs were often trained. But it's not very efficient. These vectors are enormous and sparse, meaning mostly empty. More importantly, they don't capture any semantic relationship between words. The one-hot vector for quote cat end quote is just as different from the vector for quote kitten end quote as it is from the vector for quote submarine end quote. The model has to learn from scratch, just from context, that quote cat end quote and quote kitten end quote are related. A much more modern and powerful approach, which we will dedicate an entire future episode to, is word embeddings. In this method, we use a different neural network to learn a dense vector representation for every word. Instead of 50,000-dimensional sparse vectors, we might have 300-dimensional dense vectors, where every number is a meaningful value. In this quote embedding space, end quote, the vector for quote kitten end quote would be mathematically very close to the vector for quote cat, end quote. The vector for quote king end quote minus the vector for quote man end quote plus the vector for quote woman end quote would actually result in a vector very close to quote queen, end quote. For today's episode, all we need to know is that each element in our sequence, whether it's a word, an audio frame, or a stock price, is first converted into a numerical vector. We'll call this vector x sub t, the input at time step t. The RNN's job is to process this sequence of vectors, one after another. The architectures we've studied so far, the multi-layer perceptron and the convolutional neural network, operate on a fundamentally different assumption. They typically assume their data is quote IID, end quote, which stands for independent and identically distributed. This is a statistical way of saying that each data point and each feature within that data point is treated as an independent event. A CNN looking at one pixel doesn't assume it's part of a time sequence with the next pixel it sees. It assumes it's part of a spatial grid. This worldview is perfectly suited for tasks like image classification, but it creates an insurmountable barrier for sequential data. Let's break down exactly why these feed-forward networks fail, and I mean really fail, in an almost comical way. Imagine you're given a task: write a summary of a 10,000-word essay on the Roman Republic. But there's a catch. You're not allowed to read it in order. Instead, someone has taken all 10,000 words, put them in a blender, and handed you an alphabetical list. Quote A, about, Brutus, Caesar, Carthage, end quote, and so on. Could you do it? Of course not. You'd have all the components, but zero context. This quote bag of words end quote approach is exactly what a standard multi-layer perceptron does. It treats its inputs as a set of features, not a sequence. The order is completely lost. It has no memory of what came before. Now let's try our powerful CNN from last episode. A CNN is good at finding local patterns, so let's say we don't shuffle the words. We just feed the essay, one word at a time, into the CNN. The CNN sees the word quote, the end quote, it processes it, then that word vanishes, and it sees the word quote Roman, end quote, it processes it, then that vanishes, and it sees the word quote Republic, end quote. Because the CNN is feedforward, its processing of quote Republic, end quote, is a completely separate event from its processing of quote Roman, end quote. It has no quote memory, end quote, to connect the two. It's like trying to understand a movie by looking at each frame individually, with a 1-second pause and a complete mind wipe between each frame. You'd see a person, then a car, then a building, but you could never piece together the narrative. This brings us to the 3 fundamental failures of feedforward networks for sequential data. The first problem is purely structural. They demand fixed-size inputs. An MLP designed to process customer data might have 100 input neurons for 100 features. A CNN for a specific image size, say 224 by 224 pixels, has a fixed input layer to match. But how would you apply this to language? One sentence might have 5 words while the next has 25. You could try to pad the shorter sentences with empty tokens to make them all the same length, but this is incredibly inefficient and feels like a clumsy workaround, not a genuine solution. It doesn't address the core conceptual problem. The deeper issue is the absence of parameter sharing across time. Imagine we did build a massive feedforward network to handle a 25-word sentence. It would have a set of weights to process the first word, a completely separate set of weights for the second word, another set for the third, and so on. This means the network would have to learn the meaning and function of the word quote bank, end quote, as in a riverbank, at the beginning of a sentence completely independently from learning what quote bank, end quote means at the end of a sentence. This is a colossal waste of resources. We intuitively know that the process of understanding a word should be the same, regardless of its position. The network should learn a single set of rules for language and apply them sequentially. This brings us to the most fundamental failure, the lack of memory. In any feed-forward network, information flows in one direction only. Like a river that never circles back, it moves from the input layer, through the hidden layers, to the output layer. There are no loops. This means the network has absolutely no mechanism to carry information from the processing of one input, let's call it x sub t, to the processing of the next input, x sub t plus 1. When it sees the word quote cat, end quote in our sentence, it has already completely forgotten that it just saw the word quote chased, end quote. Each input is a new, isolated world. This is the amnesia we spoke of, and it makes true understanding of sequences impossible. The problem isn't just a technical limitation that can be patched, it's a philosophical one. Feed-forward networks see the world as a collection of disconnected snapshots. Sequential data requires a model that sees the world as a movie. The solution, when it arrived, was both profoundly simple and deeply powerful. The idea of networks with feedback loops had been explored for years, with roots in concepts like the Hopfield network from the early 1980s. But it was in the mid-1980s and early 1990s that researchers like Rummelhart, Ellman, and Jordan began to formalize the architecture that would become the modern recurrent neural network. Their innovation wasn't a complex new type of neuron or a revolutionary activation function. It was a single, elegant architectural change, a loop. Imagine a standard hidden layer in a neural network. It takes an input, multiplies it by a weight matrix, and produces an output. Now picture an arrow emerging from that layer's output and looping right back around to become one of its inputs for the next step. That single, recurrent connection is the invention. It's a channel for the network to talk to its future self. It creates a pathway for information to persist, to be carried forward in time. This loop is what makes a neural network quote recurrent, end quote. Now, a loop can be a confusing thing to think about. How does it actually compute anything? The clearest way to visualize an RNN's operation is to quote unroll end quote it through time. Let's go back to our 5-word sentence. Quote, the dog chased the cat. End quote. Instead of picturing one network layer with a confusing loop, imagine 5 identical copies of that network, laid out in a line from left to right. The first network copy, at time step t equals 1, takes the first word, quote the end quote, as its input. It performs its calculation and produces an output. But critically, it also produces a second thing, a quote message end quote, that summarizes what it just processed. It passes this message forward to the second network copy. The second network copy, at t equals 2, now has 2 inputs. The next word in the sequence, quote dog end quote, and the message it received from the first network, which contains the context of quote the end quote. It combines these 2 pieces of information, performs its identical calculation, and produces its own output. It then generates an updated message, a summary that now incorporates both quote the end quote and quote dog end quote, and passes it to the third network. This process continues down the line. The third network combines quote chased end quote with the memory of quote the dog end quote. The fourth combines quote the end quote with the memory of quote the dog chased end quote, and so on. This chain of identical networks, each processing one element of the sequence and passing an evolving message to the next, is a perfect mental model for what an RNN is actually doing. The loop is just a compact way of representing this unrolled chain. This unrolled view is more than just a helpful visualization. It's also key to understanding how these networks are trained. When the network makes a prediction at the end of the sequence and calculates an error, that error signal has to travel backward through the entire chain, from the last copy all the way to the first, updating the weights at each step. This process is fittingly called backpropagation through time. So, what exactly is this quote message end quote being passed from one time step to the next? This is the absolute core concept of the RNN, and it has a specific name, the hidden state. The hidden state, often denoted mathematically as h sub t for the state at time step t, is a vector of numbers. You can think of it as the network's memory. It is a compressed, numerical summary of all the relevant information the network has processed in the sequence up to that point. It's the network's evolving understanding of the context. Let's use a more human analogy. Imagine you're reading a long, complex novel. You aren't just processing each word in isolation. As you read, you are constantly building and updating a mental model of the story. You're tracking the characters, their relationships, the key plot points, the setting, and the overall tone. This rich, evolving mental summary is what allows you to understand the significance of a new sentence in the context of everything that came before. The RNN's hidden state is the mathematical equivalent of this mental model. As it processes each word, it updates this vector to incorporate the new information, creating a richer summary of the sentence so far. This analogy is great for intuition, but we are here to go quote under the hood, end quote. So let's look at the actual calculation. Let's build this update mechanism from its components. At any given time step t, the RNN cell's entire job is to compute the new hidden state, h sub t. To do this, it needs 2 and only 2 pieces of information. First, the brand new input vector for this time step, x sub t, and second, the old hidden state from the previous time step, h sub t minus 1. Here is the recipe, step by step. First, the network processes these 2 vectors separately. The new input, x sub t, is multiplied by a weight matrix. Let's call this w sub xh, the quote input to hidden end quote weights. The job of this matrix, which the network will learn, is to determine quote what is the importance of this new piece of data. What parts of this new word chased are relevant for my memory? End quote. At the same time, the old hidden state, h sub t-1, is multiplied by its own weight matrix. Let's call this w sub hh, the quote hidden to hidden, end quote weights. This is the recurrent weight matrix. Its job is to determine, quote, what is the relevance of my old memory? How much of my previous context, the dog, should I carry forward? End quote. Now the network has two results. It adds them together, along with a biased term b sub h, just as we've seen in every network since episode 11. This addition is the magic moment. It's the integration of new information with old context. But we're not done. This resulting sum could be any set of numbers. They could be large, they could be small. If we just pass this sum along, the numbers in our hidden state could grow bigger and bigger and bigger at every time step, until they, quote, explode, end quote, to infinity. We need to control our memory. So we take this sum and, as our final step, we pass it through a nonlinear activation function. As we discussed in episode 14, this squashes the output. For a simple RNN, the function of choice is almost always the hyperbolic tangent, or TANH. Why TANH? Because it squashes any input, no matter how large or small, into a very specific range between -1 and +1. This is vital. It means our hidden state vector h sub t is a quote normalized end quote memory. It's a vector of numbers, all between -1 and 1. This keeps the memory stable and bounded. It forces the network to learn to represent its entire understanding of the past within this fixed numerical range. And that's it. The output of that TANH function is the new hidden state h sub t. This new vector, which now contains the synthesized understanding of, quote, the dog chased, end quote, is passed to the output layer to make a prediction if needed. And most importantly, it is passed forward to the next time step, t+1, where it will become the, quote, old, end quote, hidden state h sub t-1 for the next round of calculations. This brings us to the second stroke of genius in the RNN's design, parameter sharing. In that update calculation we just described, there were two key weight matrices, W sub xh for the input and W sub hh for the recurrent connection. The crucial rule of an RNN is that these weight matrices are the exact same at every single time step. The W sub xh used to process the first word, quote the, end quote, is identical to the W sub xh used to process the fifth word, quote cat, end quote, or the 50th. The W sub hh used to update the memory at t=2 is the same one used at t=50. This is a profound departure from our hypothetical feed-forward network that needed unique weights for every position in the sequence. Parameter sharing provides two massive advantages. First, it dramatically reduces the number of parameters the model needs to learn. This makes the network far more efficient to train and much less prone to overfitting, as it has a smaller, more constrained set of rules to discover. Second, and more importantly, it allows the network to generalize to sequences of variable lengths. Because the update rule is the same regardless of the time step, the RNN can process a sentence with 5 words or a paragraph with 500 words without any change to its fundamental architecture. It isn't learning a static map from a fixed input to a fixed output. Instead, it is forced to learn a true, reusable process. It's learning a single, recursive function for how to update its memory given a new piece of information and its past memories. This is a much deeper form of generalization. The network isn't just learning to recognize patterns across different examples. It's learning a rule that is invariant across time. It's learning something akin to a small, recursive algorithm, a fundamental logic of how to integrate new information into an existing context. With this architecture of memory in place, RNNs can be configured to solve a wide variety of problems, depending on how we map input sequences to output sequences. This gives rise to a small zoo of common RNN structures, each tailored for a specific kind of task. The simplest structure is a many-tune architecture. Here, the network reads an entire sequence of inputs, but only produces a single output at the very end. A classic example is sentiment analysis. The RNN processes a movie review word by word, building up an increasingly nuanced understanding of the text in its hidden state H sub t. It actually produces an output at each step, but we just throw them away. After reading the final word at time step t, it uses that final comprehensive hidden state H sub t to output a single prediction. A score from 1 to 5, or a simple positive end or negative end label. The journey mattered, but only the final destination was the answer. Conversely, we have the one-to-many architecture. In this case, the network takes a single fixed input and generates a sequence of outputs. Image captioning is a fantastic example. First, a convolutional neural network, like the ones we just mastered, processes an image and distills its contents into a single feature vector. This vector is then fed as the initial hidden state, H sub 0, to an RNN. The RNN is then given a special start-end token. It combines the image memory H sub 0 with the start-end token and generates the first word, a end. Now for the next step, that word a end that it just generated is fed back in as the input for t equals 2. The network combines its memory with a end and generates dog end. That word dog end is then fed back in as the input for t equals 3. It combines its memory with dog end and generates chasing end. This continues, a dog chasing a cat in I end until it generates a special end of sentence end token. Then there is the many-to-many architecture, which comes in two main flavors. The first is synchronous, where there's an output for every input. Think of video classification on a frame-by-frame basis. For each frame of video that comes in, input X sub t, the network outputs a label describing the action in that specific frame, output O sub t. The input and output sequences have the same length and are perfectly aligned in time. The more complex and powerful version is the asynchronous many-to-many model, often called a sequence-to-sequence or seq-to-seq architecture. This is the workhorse behind machine translation. Here, the task is to convert an input sequence into an output sequence of a potentially different length. For example, translating the three-word English sentence "How are you?" end into the two-word Spanish sentence "Como estás?" end. This is handled by a clever design using two RNNs. The first RNN, called the encoder, reads the entire English sentence one word at a time. Its job is just to read. It doesn't produce any outputs we care about. It just processes the whole sentence and compresses its full meaning into a final hidden state vector. This is sometimes called the thought vector end or context vector end. Then a second RNN, the decoder, takes that final context vector from the encoder as its initial hidden state. This thought end is all the information the decoder gets about the original sentence. The decoder is then given a start end token and begins to generate the Spanish sentence word by word, just like our image captioning model. Como end estás end. This encoder-decoder structure was a major breakthrough, allowing RNNs to tackle complex transformation tasks where the input and output don't have a simple one-tune correspondence. However, let's pause on this thought vector end for a moment. This idea is both brilliant and deeply flawed. The encoder is being asked to compress all the information from a potentially 50-word sentence, all its nuance, grammar, and meaning, into one single fixed-size vector, maybe 512 numbers long. The decoder must then reconstruct a perfect translation from only that compressed summary. Imagine trying to summarize the entirety of War and Peace into a single paragraph, and then asking someone to rewrite the entire novel in French, using only your paragraph as a reference. It's an impossible information bottleneck. This was a massive problem for early seq-to-seq models. They worked well for short sentences, but for long sentences, the quote thought vector end quote would just become a muddled, average-sounding summary, and the translation quality would plummet. This very problem is what forced researchers to invent the quote attention end quote mechanism, which is the heart of the transformer models we'll cover in episode 20. But even with these flaws, these abstract structures power technology that many of us use every day. The speech recognition in your smart speaker or voice assistant uses RNNs, or their descendants, to transcribe the sequence of sound waves from your voice into a sequence of words. Language translation apps are a direct application of the seq-to-seq models we just discussed. Even financial institutions use RNNs to analyze time series data from the market to forecast future trends or detect anomalous trading activity. The simple loop gave machines a way to understand the flow of information, and in doing so, unlocked a new universe of applications. Now, hearing all of this, you might be led to a very common and intuitive misconception that an RNN's memory is perfect, like a computer's RAM, capable of flawlessly recalling information from the distant past. It seems logical that the hidden state, by carrying information from the very beginning of a sequence all the way to the end, would have an infinite memory span. This is completely, fundamentally false. In reality, the memory of a simple RNN is tragically short-lived. It's less like a computer's RAM and more like a human's, well, a goldfish's. It struggles profoundly to connect information across long time intervals. This critical weakness is known as the problem of learning long-range dependencies. The network might learn that quote San end quote is often followed by quote Francisco end quote. That's a dependency of one step. It might even learn quote the clouds are dark, so it will end quote rain end quote, a dependency of a few steps, but it will never learn from this quote I was born in France end quote. Then, after 2 paragraphs of text about my childhood, my education, and my job, the text continues, quote, as a result I speak fluent end quote. By the time the network reaches the word quote fluent end quote, the information about quote France end quote is gone. It has been completely washed out of the hidden state by the hundreds of intermediate words. The network will be no better at guessing quote French end quote than it would be at guessing quote Spanish end quote or quote Klingon end quote. The technical reason for this fragile memory is one of the most famous challenges in training deep neural networks, the vanishing gradient problem. To understand this intuitively, let's use our quote unrolled network end quote visualization. Remember that training an RNN involves backpropagation through time, where the error signal from the end of the sequence must travel all the way back to the beginning to update the weights. Imagine a long line of people playing the game of telephone, or quote whisper down the lane, end quote. The first person whispers a message to the second, who whispers it to the third, and so on. By the time it reaches the last person, the message is often hilariously distorted. Now imagine you're the coach, standing at the end of the line. You hear the final incorrect message, quote, the purple monkey flies at midnight, end quote, and you know the correct message was, quote, the quick brown fox jumps over the lazy dog, end quote. You need to send a correction all the way back to the first person. You whisper the correction to the person next to you, quote, you were wrong. The word was dog, not midnight. End quote. That person whispers to the person before them, quote, heard wrong dog. End quote. The next person hears, quote, word dog. End quote. The next person hears, quote, og. End quote. By the time your correction signal reaches the person at the very beginning of the line, it has become a faint, meaningless mumble. They barely hear it, so they have no idea what they did wrong. They don't learn. This is exactly what happens to the error signal. The gradient, in a deep RNN, as it propagates backward from the end of the sequence, say word 50, to the beginning, word 1, it has to pass through that recurrent calculation, and specifically that TANH activation at every single time step. Let's dig into the math of this because it's the key. In episode 13, we learned that backpropagation relies on the chain rule. You multiply derivatives together as you go backward. In a normal feed-forward network, the quote chain end quote is as long as the network is deep, maybe 10 or 20 layers. In an unrolled RNN, the quote chain end quote is as long as the sequence. A 50-word sentence creates a 50-layer deep chain. A 1,000-word document creates a 1,000-layer deep chain. Now, what is the derivative of the TANH function? A property of this function is that its derivative is always a value less than 1, except at the exact point 0, where it is 1. This means that every single time the gradient signal passes backward through a TANH function on its long journey back in time, it gets multiplied by a number less than 1. Take a number, say 0.9, multiply it by 0.9, you get 0.81, multiply by 0.9 again, 0.729 again, 0.656. After just 50 steps, that 0.9 has shrunk to 0.005, it has vanished. This is the vanishing gradient problem. The gradient signal from the distant past effectively shrinks to 0. The network receives no information about how its early calculations, at word 1, contributed to the error at the end, at word 50. As a result, it cannot learn long-range dependencies. Its memory is, by mathematical necessity, short-term. This problem is a direct and unavoidable consequence of the RNN's core design. The very mechanism that gives the RNN its power, the recurrent application of the same squashing function over and over again, is the same mechanism that causes its learning signal to decay over long distances. The architecture's greatest strength is inextricably linked to its greatest weakness. On rare occasions, the opposite can also occur. If the recurrent weights W sub HH are very large, the signal can grow exponentially as it travels backward. This is the exploding gradient problem. This is like the telephone game where everyone shouts the message, and by the end, it's a deafening, distorted roar. This is actually easier to solve. We can use a simple brute force technique called quote gradient clipping. End quote. We just tell the network, quote, if any gradient value is bigger than, say, 10.0, just set it back to 10.0. End quote. It's an ugly hack, but it stops the network from blowing up. But you can't quote clip end quote a number that's already 0. The vanishing gradient is a much more insidious and fundamental challenge. Before a true solution to the vanishing gradient problem was found, researchers developed a clever workaround for certain types of tasks. This is the bidirectional RNN. The idea is simple but effective. Instead of processing a sequence in only one direction, from past to future, a bidirectional RNN uses two separate RNNs that run in parallel. One RNN processes the sequence from left to right as usual, capturing the quote past end quote context. The second RNN processes the same sequence from right to left, from the end to the beginning, capturing the quote future end quote context. At any given time step t, the final output is a combination often just a concatenation of the hidden states from both the forward RNN and the backward RNN. This gives the model a richer, more complete view of the context surrounding each element. For example, in the phrase "a teddy bear," the word "bear" helps us understand that "teddy" is not a name. A forward-only RNN sees "teddy" first and has no idea. But the backward RNN, which starts at "bear" and moves left, does know about "bear" when it arrives at "teddy." Similarly, in "that was a dull movie," the word "dull" is clearly negative, but in "there was never a dull moment," the same word contributes to a positive sentiment. A standard RNN sees "dull" and immediately leans negative, and might not be able to correct itself by the time it sees "moment." A bidirectional RNN, when it is processing the word "dull," has already seen "never" from its backward pass and "moment" from its forward pass. It has the full context and can correctly interpret the phrase. It's important to note that this doesn't solve the vanishing gradient problem. The memory of each individual RNN is still short, but it helps by ensuring that for any point in the sequence, the distance to some relevant context, either in its past or its "future" is effectively cut in half. This technique is incredibly useful for offline tasks like text analysis or translation, where the entire sequence is available at once. But it's obviously not applicable for real-time prediction, like your smartphone keyboard, where the future is, by definition, unknown. So, as we conclude our deep dive into the first generation of recurrent networks, let's take stock of what we've learned. We began by recognizing the fundamental limitation of feed-forward architectures, their amnesia, their inability to comprehend data where order is the key to meaning. We then introduced the recurrent neural network, an architecture whose elegant design, a simple loop, endowed it with a hidden state, a form of memory. We saw how the principle of parameter sharing makes this architecture both efficient and flexible, allowing it to learn a reusable process for understanding sequences of any length. This was a monumental paradigm shift, the first step toward building AI that could understand narrative, process, and the flow of time. Yet we also uncovered a tragic flaw in this simple memory. The very mechanism of recurrence that created the memory also caused it to be fleeting. The vanishing gradient problem meant that the echo of the past faded too quickly, preventing the network from learning the long-range dependencies that are so crucial for deep understanding. But this flaw should not be seen as a failure. It was a critical scientific discovery. It illuminated the profound challenges of training deep sequential models, and in doing so, it set the research agenda for the entire next decade of AI. It created a clear and urgent question for the field: how do we build a better memory? We've seen the power and the tragic flaw of the simple RNN's memory. So, how do we build a network with a memory that can last? How do we give it the ability to selectively forget irrelevant details and protect important information over hundreds or even thousands of time steps? The answer lies in a more complex architecture, one inspired by the logic of digital circuits, with internal "gates" that meticulously control the flow of information. Next time, we will deconstruct the long short-term memory network, or LSTM, the architecture that solved the long-term memory problem and truly unlocked the potential of sequential AI. The simple idea of feeding a network's output back into itself was more than just an architectural trick. It was the moment we started building models that don't just see the world, but experience it as it unfolds, one moment at a time.
You've been listening to AI Deconstructed, Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.